Dmitry works as a computational scientist at the San Diego Supercomputing Center at UCSD. Take it away, Dmitry.
Hello, can you hear me?
Yes, we can, thank you.
Okay. So I'm going to talk about portable framework for multidimensional spectral transforms at large scale. I will not spend a lot of time explaining the importance of these transforms, but I will just mention briefly. First of all, spectral transforms include fast Fourier transforms. And this is a very ubiquitous algorithm in many areas of science and engineering. Traditional big users of fast Fourier transforms, or FFTs, is DNS turbulence simulations. But also they are used in many other areas. I'll just name a few, but this is not an exhaustive list. Seismic simulations, acoustics, oceanography, quantum physics, molecular dynamics, X-ray crystallography, and so on. And as such, this algorithm is responsible for a large portion of cycles consumed on modern supercomputers. It has some challenges in terms of bringing it to exascale. So it can be a limiting factor for quite a number of codes to bring them to exascale. So here are the motivating questions for this work. What can be done to reconcile spectral transforms and exascale? What can be done to increase the range of use beyond traditional DNS turbulence codes? And can performance and flexibility somehow be combined? And by the way, we have, you should probably see a poll being started. You can take a look at the poll. There are some common properties of the spectral transforms, and namely that they are easily broken down into independent one-dimensional transform components. For example, the 3D FFT, broken down into independent 1D transforms. Each 1D transform is a non-local, essentially non-local. So it's best suited for node local implementation where no inter-processor communication takes place. But then the algorithm reshuffles the data among processors between the consecutive 1D transformations. And it has been shown that this algorithm, it contains global communication all-to-all, and so it's limited by bisection bandwidths. That's what makes it difficult to bring to exascale. And it's also severely limited by node memory bandwidths. So the goal here is to create a library to encode the common structures for all these algorithms. As I said, they go beyond FFT. So, and many codes have their own implementations of these algorithms. So the question is, why do we have to reinvent the wheel? We can just create a library for kind of to spread the information and good knowledge about this, and save a lot of work for researchers. Here's a diagram for a three-dimensional FFT with 2D processor decomposition. So imagine you have a three-dimensional grid. You want to decompose it in processor space, let's say in 2 dimensions. So you have a 2-dimensional processor grid that will end up with one dimension is here in X dimension. All will be local. The X dimension here all will be local, but Y and Z dimensions will be distributed among processors. So this configuration we call it X pencils. So we can start here and we can perform a 1D FFT in X because all X is local. Then we reshuffle the data by all-to-all exchange in groups to rearrange the data in Y pencils. So here Y local, we can do FFT in Y direction. Then we reshuffle again to make a Z pencils and perform 1D FFT in Z. This is so this is a forward FFT transform. It involves 3 local one-dimensional transforms and 2 exchanges, transposes. And for inverse transform, we can just retrace the steps. I should be fair and say that there is, of course, many open source implementations already available for 3D FFT, many libraries, as well as many proprietary ones. Each has their own areas of strengths. Traditionally, they're focused on DNS turbulent style codes. And so they have kind of a narrow range of data layouts that they use. Very few support overlapping communications computation that I will talk about. Just a few of them support GPUs. And so there is a number of improvements that can be done and to bring this type of software to modern exascale standards. I want to talk about the expanding functionality as well. The spectral transforms, as I mentioned, they really encompass a diverse ecosystem with varied boundary conditions, varied data types, varied data layouts, varied processor decompositions. Also, there are some special cases that present an opportunity for optimization, such as proof transforms. Proof transforms are cases where you don't need the whole to preserve the whole output of a transform. Just a part of it will do. Multivariable transforms, high order operations such as derivatives, convolutions, Laplacians, and so on. So here are the main design challenges for this work. I'm going to be talking about a package called P3D FFT++. That's the main subject of this work. The design challenges include, first of all, maximizing performance at exascale, pre-exascale platforms, which, as we know, tend to be heterogeneous platforms, while preserving portability, having ease of use, and having this universal functionality that I mentioned in previous slides, trying to make them as flexible as possible so they can be, to increase the scope of application. And here are, oh, by the way, yeah, I want to mention again that the poll, you should see a poll. If you are willing, you can look at that, and it asks you about, it asks you to rate different design criteria for modern numerical software library. Here are the features of P3D FFT at a glance. It optimized for large core counts. Currently, it implements one-dimensional and two-dimensional processor decomposition. We are also working on a three-dimensional decomposition in future. As I mentioned, it has a flexible data layout. We are working on having pruned transforms capability, multivariable transforms with overlapping communication with computation. It is GPU enabled. Currently, it's CUDA. In the future, we will also implement an interface that will enable it to run on AMD GPUs without loss of generality. And this will also include the overlap offload. 3D transforms are currently implemented. In the future, we may actually work on four-dimensional transforms, which have some areas of application. And finally, it will feature auto-tuning framework, because the use cases are so varied and platforms are so varied, it's not possible to know which algorithm will work best in each situation. So we will have an auto-tuning. And as I mentioned, it will have high order functions. So it's an P3D-FFT++ is an open source package with examples, documentation. It builds on the knowledge that we gained from previous work on P3D-FFT package, but it's a distinct effort in this distinct code base. It is object-oriented module design, and it hides platform and implementation details, how the flexible data layout, auto tuning, high order and low order functions. It's written in C++. P3D-FFT was written in Fortran originally. So this is C++, but it has both C and Fortran interfaces. We want to use C++. We want to use all the convenient features of C++, but we don't want to minimize performance. So the compute-intensive parts are written in C-style code to optimize performance. It uses MPI. It uses CUDA currently for GPU interface, but this can be easily generalized to, as I mentioned, to other interfaces. It supports general transform types beyond FFT and general data types. Similar to most libraries, it offloads one-dimensional transforms to a specialized library, such as FFTW, ESSL, or QFFT. Again, there is no need to reinvent the wheel. These are specialized, highly optimized libraries already existing for one-dimensional transforms. It uses C++ features, again, to make it convenient, extensible, modular. This is a diagram of overview of the structure of the library. At the very top, we have high order features that I mentioned: correlation, convolution, spectra, derivative, gradient, divergence. Then on the next level, there is 3D transforms and in the future 4D transforms. They can be implemented as a 1D, 2D, or 3D decomposition processor space. It is built on top of 1D transforms that I mentioned. They are implemented by using specialized libraries and transposes. There can be different multiple implementations of these transposes, but eventually it's all built on top of MPI. So here I was wondering if we can stop the first poll and start the second poll. Also, I don't know if it's possible to see the results of the first poll. We'll be curious. Is it possible?
There is a bit of a delay on that, Dmitry. So we put the first poll up, but I just don't think there are any responses as of yet.
Okay, good enough. So we continue. Can we start the sharing the second poll, which asks about what features would you like to see in a modern library for spectral transforms? A few words about library structure. It can use several data types, real complex, of course, single and double precision currently. Function classes expressed as C++ templates with interfaces for C and Fortran. Dimension has the lower level 1D transforms and high level functions 3D transforms that are built on top of 1D transforms. This is expressed in the most general way. It can be easily extended to other types of transforms. The execution model is similar to FFTW, where you are in the initialization phase of your program, you call a planner function. So it initializes that transform, initializes all data. And then these plans can be called multiple times during the body of the execution. Here's important area here is to describe a metadata descriptor called grid. Basically, this is a class that describes data grid size and properties. It describes what kind of a processor grid is used for decomposition. It describes local memory layout. So for example, it can be, how do you store the 3D array in memory? It can be stored in order of XYZ, or ZYX, and so on. There are 6 permutations. And also, how do you map, how exactly do you map the data grid onto processor grid? So these are all important, and you have to define this metadata to go along with your array. But it allows for the most general data layout that you can consider, I believe. Here is an example of usage. Here we have the initial processor grid, let's say 2 by 4 processors. This is initial memory ordering, basically default ordering XYZ. This is the destination grid, again 2 by 4, but now different indices are decomposed. With destination memory ordering is reversed. This corresponds to Z pencils. And this is global grid dimensions. We just initialize the grid variable with these parameters for the initial grid and the final grid. And next we need to define what transform do you want to describe here. So let's say we're interested in real to complex 3-dimensional FFT. So we need to define it as a 3-dimensional transform with the following types. One is, the first one is real to complex 1-dimensional. The second is complex Fourier transform, and the third again is complex Fourier transform. So this defines real to complex 3-dimensional transform. Here we define the 3-dimensional transform class, and we initialize this as a constructor for the class, which also includes, as I mentioned, includes planning. So all you need to do is just give the initial metadata descriptor, the destination grid, and the transform type. Now we're ready to allocate data, initial and final data, initialize the input array, and here we're ready to execute. Call the execution function of the transform type, 3D FFT transform. So it's very simple. It's easy to use, but I believe it's one of the most general descriptions. We have GPU implementation. Currently, it's CUDA. It uses QFFT for 1-dimensional FFT. It also uses QTensor, which is an NVIDIA library, for local memory transposes. And the work on the way includes asynchronous operations, operating, overlapping compute and transform, and also future work will include additional interfaces to include AMD GPUs. I want to talk briefly about performance leveraging for special cases. Since, as I mentioned, Fourier transforms are notoriously difficult to scale because they stress bisection bandwidths. So we need to try to somehow minimize damage. So in the cases where pruned transforms are needed, you don't need to preserve all of the output, only part of the output. That allows opportunity to save that bisection bandwidths and kind of spread it further and improve performance So that will be a specialized case. An extreme example of that is sparse Fourier transforms. Another area of optimization is to combine multiple transforms into a single call. First of all, it allows us to aggregate messages. And secondly, we can overlap communication with computation by staggering computation and communication stages for these different transforms. There are also a number of other optimization features that we are implementing, basically reducing the memory read and writes, because as I mentioned, memory bandwidth is really severely stressed. Reducing cache, reducing array copies, and so on. I don't think I have time to really go into detail here. A preliminary performance study, we compare P3D-FFT with P3D-FFT, which is the previous incarnation written in Fortran, and having kind of a limited data layout options. We see performance is very similar, and its case scales reasonably well, at least in a moderate range of core counts. Some package details, it has a configure script for easy installation. It has many examples in C++, C, and Fortran. These example programs can be used for both correctness tests and for benchmarking. There is a unit testing framework, and there is a documentation. I want to show it briefly here on the documentation page. It has a tutorial, and it has separate references for C++, C, and Fortran. In conclusion, this work, in this talk, I've described a new open source package, P3D-FFT++, that aims to bring high performance, to bridge high performance with ease of use and increase use range. It is object-oriented. It has object-oriented design and heterogeneous execution. The preliminary performance is on par with P3D-FFT and similar libraries. There is a future work going on in a number of important directions in terms of overlapping communication computation, in terms of overlapping GPU transfers, utilizing pruned transforms, high order functions, and auto-tuning. So I want to acknowledge that this is supported by NSF, and work done on NSF and DOE platforms. I want to stop here and invite you questions, of course, and also to consider how does FFT++ fit in your project. I'm really open to discussing future directions of this work. I'm open for contributions, suggestions for features. You can email me, or you can leave your email. And I have a third poll. Can we please have the third poll? And you can leave your comments and your email there. Thank you very much.